All right, welcome back. We'll talk a little bit about some density definitions and applications of crystals in some common materials. So here's the outline. I'll follow it. What I'd like to highlight here is, as we talked about unit cells, I mentioned primitive cells, like an atom is, there's just a single atom in the cell. How do you think about that? And here's a little image that helps you think about it. So here's a simple cubic lattice, one of the simplest Bravais lattices. And there's the cube, and you have atoms on the corner of each cube. And you repeat that cell, and you can make any space-filling group on this lattice. Now, the picture here with the red ball and the surfaces throughout show you that this single atom is, in a way, shared by 8 other cells. So, if you will, this single atom on the corner, it belongs, only 1/8 of it belongs to a specific cell, but you have 8 corners. That means you have 1 point per cell. And again, of course, this depends on the definition per cell, but we'll try to wrap our heads around that on these corner elements or face elements, an atom there might only belong partially to a specific unit cell like this. So let's look at, so that's points per cell, how many points are in the cell. And now we're talking about a number density. And the number density means here we have 1 atom per unit cell, and we divide by the volume of that cell. And let's say we measure it in cubic centimeters, then and A were in cubic centimeters, so it's 1 over A cubed, and that's points per cubic centimeter. And that does not depend on the cell definition. Meaning, at the end, a physical material, given size of it, regardless of how you define the cell, has a number density. So that's a thing to keep in mind. All right. Now, there's another density we want to look at. That's the packing density. And the question is, how much volume is really filled up with these atoms? So let's consider a simple cube again. And we take a perfect sphere as an atom, and we make these spheres as large as possible. So for the simple cube, you can clearly see that you can make the radius of each of these atoms half the length of the unit cell A. So the radius is A over 2. And the volume of a sphere is, of course, 4/3 pi r cubed. And now we're going to calculate the packing density. The packing density is the volume filled with these spheres over the total volume that is available. All right, so we have 1/8 of an atom and 8 corners. And so we have really 1 atom per unit cell. It takes the volume of 4/3 pi r cubed, and we divide by the total volume of the cell, and we get pi over 6. That's 52%. So that means that if you have this simple cubic lattice and you fill it with spheres that are half, their diameter is half the lattice length, you only fill 52% of the space. So 48% is air in this case. All right, and that is typical for crystals and amorphous materials. And that does, again, not depend on the cell definition. So you can define a larger unit cell, for example, but the physical quantity of a packing density is a physical description that you can measure as well. And that is independent of the basis representation that you chose for a mathematical representation. So let's go into a couple other examples where we deal with densities. So here we have another issue that we in devices often deal with surfaces. And we have to measure how many atoms are on a surface, because that influences how many bonds are at the surface, etc. So let's look at the simple cube again. So I'll look at the top surface like this, and we will compute an areal density. So in this area on the top surface of a cube, we have 4 corners, and each atom is part of 4 other surfaces. So there's a quarter per corner, but you have 4 corners, and you divide by the total area that's available. So that's 1 over A squared. So the areal density is 1 over A squared in this cubic lattice on this particular surface. But there could be other surfaces. There could be surfaces on the diagonal here. And we'll describe on how we, our nomenclature and how we label those kind of surfaces a little bit later. In this one, we also have a quarter atom per corner. We have 4 corners, but one of the lengths is square root of 2 A squared. So this is supposed to be square root of 2 A squared. So 1 over square root of 2 A squared. So the total areal density is 0.7 over A squared. So it is smaller than the surface here in blue. So the areal density of atoms in the green surface is smaller than the areal density of the blue. And intuitively that makes sense, because you can visually see that the green surface is actually larger than the blue surface, but it contains the same amount of atoms. So the areal density becomes smaller. So if you looked at the crystal here from in a slice, if you had a slice of this crystal in this direction, and you somehow were able to look at that surface, you would see overall less atoms on that surface than if you took a different cut in a different line here in the blue surface. Okay? So cutting a crystal in certain directions would matter in this case. All right, I'll go through a couple more examples of some of these points per unit cells, and then we'll have some exercises and quizzes where you get to wrap your head around this. So this is, let's look at BCC, that stands for body centered cubic. So there's a cube with an atom in the body in the center. So you have, just in the simple cube, you have 8 corner atoms, and you have 8 corners. So that gives you 1 atom, and you have exactly one atom in the middle. So this BCC has 2 atoms per unit cell. Let's look at FCC, so face-centered cubic. So it's a cube, and you have an atom on each of the 6 faces. Again, you have 8 corner atoms, 1/8 of the atom belongs to the cell. You have 6 faces, but each atom there is shared between 2 faces. So plus 1/2 times 6, so an FCC cell has 4 atoms per unit cell. I'll finally get to the hexagonal closed-packed Bravais lattice. It's described by these basis vectors A, B, and C. C is typically the growth direction, and A and B are really typically the same length. Now let's look at the points per cell in the hexagonal closed-packed. So let's focus on the atom with a red arrow. So we have 2 of those surfaces, and each atom that is packed, it's in the middle, is shared between 2 faces. All right, now let's imagine we repeat this cell in the lateral directions, and we want to figure out how many of these atoms on the corners are shared. All right, so if we focus on an atom here, let's say this guy here, it is being shared by 3 different neighboring areas, right? So that atom is shared by 3, and plus it's shared up and down in the surface, so half, but we have 12 of those atoms at these corners. So numbers of atoms in that cell on the corners are 2. So that means this hexagonal closed-packed system has 3 points per cell. So you have to walk your way through carefully to understand how many points per cell do you have. All right. So that gave us the definitions of some number packing and areal densities, points per cell. Let's look at some common crystals. And here is one to start with, that's sodium chloride. And let's look at this one more carefully. In the prior sections, we had talked about Bravais lattices were the basis in graphene, and the more pictogram on the top right. And we established a recipe on how to create a Bravais lattice out of these repeated basis sets that might be more complicated. So combine a complex component into a single basis and then repeat that basis. All right, so let's look at this rock salt. That is sodium chloride. It's your normal household cooking salt, right? And you see them every day. It's crystals. I'm not sure if you looked at them carefully. If you ever been to a salt mine, you can get big chunks of this salt, and you can see how the surfaces cleave in certain directions. And at first glance, it looks like a simple cubic cell, right? I mean, it looks like a perfect cube. But if you look more carefully, you can see that the atoms see different environments. So you have sodium here, here, and here, and here. And you can see that each of the elements on that hypothetical simple cube sees different environments. So therefore, that is not a Bravais lattice by itself. Okay, so but you can establish a basis set that consists of a sodium and chloride atom and establish a basis of 2 atoms, and you fill that, and now you have an arrangement here in red that is an FCC lattice. So it's face-centered cubic, and in that lattice, it looks as if you're not representing chlorine explicitly, but it is part of the basis. And as you repeat that basis, you build up the chlorine in that crystal as well. So rock salt, very common crystal, is an FCC with a basis of 2 atoms. Here's another one that we deal with in electronics very often. It's gallium arsenide, and actually silicon is very similar. So you have, here's a typical textbook example of a unit cell. Let's figure out how many atoms are in this unit cell, and let's look at the typical arrangement. So white are the arsenic atoms, and highlighted here in red and yellow is the corner atom as arsenic, and in the inside you have gallium, the yellow one. If you look diagonally across the cell, you have another arsenic atom, but it does not have on the same axis quarter, 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 meaning going in a quarter here, going in a quarter here, and a quarter up. It does not have a gallium neighbor. So there is, if you will, a void here. There is no gallium atom here. So it sees a different environment. like this. So this by itself is not a repeated Bravais cell. So let's see how we can construct a Bravais cell for this. So again, we can highlight the corner elements here of arsenic and find its equivalent examples and count the numbers of atoms in the cell. So if you just are after the number of atoms in this cell, we can count that. But this is not truly the Bravais lattice of the repeated cell. So we have a tetrahedral structure. We have 8 atoms per cell on the corners. They go over 1/8. All right. And then we have, on each face, we have gallium atoms. We have 6 faces and half a gallium each. Plus we have, arsenic. My mistake. So here we have arsenic. And then on the surface we have arsenic, and then we have the gallium atoms here. So in total, we have 8 atoms in this unit cell. All right, and it's arranged in a tetrahedral structure, as you can see if we pull this out here. So this builds a tetrahedron, and we of course have seen tetrahedrons like this. And let's look at the gallium crystal in a different view in Crystal Viewer. That's a nano-hub tool. I'll invite you to use it. There is a couple of exercises we'll do with this tool. And here's in red, you see the atoms that are exposed on the surface. They're colored. Let's take away the surface atoms and let's take away the bonds of this crystal. And let's focus just on one species in this crystal. And let's focus on a few. So we keep within the same species, but what we'll do is we'll throw a few atoms away. And now we can draw an FCC cell through that. So for visualization, we can now see that we can make up this crystal of one species with an FCC cell. Let's count the number of atoms. Again, FCC we already counted earlier. 1/8 of an atom on each corner, but it's shared amongst 8 cells, so 1. We have 6 faces, and the atom is part of half of the cell, and it's shared between 2 neighboring cells. So we have 4 atoms per unit cell. So let me swipe those atoms away that are not part of the cell, and let me bring in the other species again. And now I can do the same process of focusing on a few of the blue species, and I can draw the same unit cell for the blue. All right, so let me look at just the atoms that are part of these cells. So here for the purple and for the brown, and you kind of get the feeling that we can represent this gallium arsenide crystal with 2 FCC cells. Each has 4 atoms in each unit cell. So Zinc-Blende is therefore, that's the crystallographic name for this particular crystal structure. Zinc-Blende has 2 FCC bases separated by a vector of 1/4, 1/4, 1/4. Right? So that gives you a way to describe the gallium arsenide crystal. Now, diamond or silicon is really the same crystal structure. It has 2 FCC bases, but just a single species in it. So there's all the atoms in that crystal are silicon rather than gallium arsenide, but the crystalline structure is identical. So it's 2 FCC bases separated by quarter, quarter, quarter. Lastly, we'll look at hexagonal closed-packed cadmium selenide. So here's a crystal of cadmium selenide, and we'll again count the number of atoms in this cell. So we have the top surface atoms, similar to the hexagonal structure we looked at before. And we have another species here, the sulfide, in the same hexagonal structure underneath. And then at the bottom of that cell, we have again the cadmium. All right. So let's look on the cadmium first. So it's a hexagonal on the surface, like what we highlighted here. And we can have interleaved in there the other cadmium cells. So you have a hexagon structure in a plane, and you have a displaced other hexagon like this. So what you have is, for cadmium, you have, again, as we counted before, we have 12 atoms that are shared in 1/6 between the cells. Then we have 2 atoms that are shared up and down. And then on the inside of this cell here, we have 3. So I just went through this here. So these are the 3 here. 1, 2, 3. That's this here. Then we have the 12 cells that are shared by 1/6 and another half. All right. So that concludes number counting, densities, areal density definitions in crystals. And in the next section, I'll talk about surfaces. Thank you.